All right, here's another video on the sampling distribution. This will be the last one from 4.1. The last of four videos, because this is a really important topic. It deserves all the time we're giving it. It's going to be the basis, the backbone for the rest of the class. So the idea with this video, unlike the previous three, is I'm just going to try to work a few examples to show you what test questions will look like when the test questions deal with the sampling distribution. So let's do it. Suppose we have, let's talk about household income. So suppose maybe mean household income in the United States is, I don't know, 60 grand with, it's going to have a huge standard deviation. Let's say the standard deviation with a standard deviation of 40 grand. Sure. I don't know how accurate these are, probably not very accurate. And you might be like, mean household income, that sounds weird. I'm used to hearing median household income when I hear this cited as like an economic indicator. That's true. Typically, people cite median household income instead of mean household income. And that's because household income is very, very skewed. I didn't mention this in the problem, but it's true. Household income is often used as like the typical example of something that is right skewed. Right? If this is income here, and here's 0, and here's 100K, and 200K, and 300K, and so on. Most people make between, I don't know, 0 and 200 grand maybe. Maybe it looks something like this. I don't know exactly what it looks like. But most people are over here on the left. However, there is a huge tail going out to the right. Right? This goes and goes and goes. Picture, I don't know, Steph Curry. We make 40 million last year or something like that. Or some CEO or some, I don't know, really some celebrity. Take your pick. There's plenty of people that make tons of money. There's a big tail going out to the right. Most people, educators, for example, are over here not making a lot of money. But some people make a ton of money and they're way out to the right. Household income is very, very, very right skewed. Although it turns out you don't need to know any of that for this problem. But because it's right skewed, people usually measure its center with something that is resistant to outliers. Right? Because since it's right skewed, you're going to have lots of outliers, think Steph Curry. And because we got lots of outliers, the center is better reported by something that is resistant to outliers, namely the median. So if we were talking about household income, it might make more sense to talk about the median household income, not the mean. However, this problem, the information we're given is about the mean. Mean household income in the United States is 60 grand. If you're reading through this problem and kind of labeling things, you might say that mu is 60 grand. I'll just say 60 and everything's in thousands. And the standard deviation is 40 grand. So maybe sigma equals 4. I'm going to put 1,000. I don't want to confuse people. Fine. And then what type of question might be asked? What is the probability of that? In a random sample of, I don't know, let's say 100 households, the average income is below, I don't know, 50,000. Sure. Suppose I asked you this question. If I asked you this on the test, there would be several parts to it. Right? The first thing I would talk about is, I'd say something like, you're going to determine the probability that in a random sample of 100 households, the average income is below 50,000 by following the steps below. And if you're reading through this problem, the fact that this is 100 right here tells you that n is equal to 100. Anyways, the steps below, what the first one would say would be something to the effect of state and justify the shape of the sampling distribution, or maybe of the relevant distribution, but I'll say sampling at this point. And so the idea here is this question is not about one household, it's about the average of 100 households. And so what that means is, since the question is about an average, we're talking about the sampling distribution, not the parent distribution. So the shape, the center, and the spread are given by this column in my little matrix here. So when it asks me to state and justify the shape of the sampling distribution, well, you can kind of cheat. The shape is going to be approximately normal. Maybe this is like answers in red. Shape is approximately normal, or just normal is fine. Maybe shape is normal. But it doesn't just say, tell me what it is, it tells me why. It asks me to tell you. It asks you to tell me. It asks somebody to tell somebody why. The shape is normal because, well, there's two possible answers. It's either going to be because the parent distribution is normal. If you read through this, there's no mention of the parent distribution being normal. And if you think deeply about it, you might be like, yeah, the parent distribution is not normal. Income is right skewed. It's certainly not normal. So the reason why is not number one here, it's number two. Right? Even if the parent distribution is not normal, that's okay as long as our sample size is large enough. That's the central limit theorem. That's what we saw with that applet, that no matter how bad we messed up that black distribution, as long as n was big enough, the blue distribution looked nice. As long as n is large enough and the cutoff we use in our class is 30, we're good. So you'd say the shape is normal because n is greater than or equal to 30, n being equal to 100. As long as you label n up here, I don't need you to tell me again what n is down here. Shape's normal because n is greater than or equal to 30. Then I would ask you a question about the center. Say something like, what is the center? Maybe of the sampling distribution. And I might even say, use the appropriate symbols or something like that, or I don't know. The point is, the symbol that you use for the center of the sampling distribution is not mu. It's mu with the little x bar in the subscript, mu sub x bar. And there's a formula for mu sub x bar. It's a really easy formula. It's just equal to mu. And mu will always be given to you in these problems. Always, 100% of the time. So mu sub x bar is the center, and it's equal to 60,000 because it's always just the same as mu. And the next question that I would ask you is, what is the, I'm getting really lazy, spread of the sampling distribution? And maybe I'd also add a note about using appropriate symbols. And if you're using appropriate symbols, you're saying the symbol for the spread of the sampling distribution is sigma with a little x bar down in the subscript. Because it's not the sigma of an individual household, it's the sigma of the sample averages, the x bars of the groups of 100. And there's a formula for that as well. And it's harder than this formula. It's not just equal to sigma, it's equal to sigma divided by the square root of n. So sigma in this case is 40,000, and n is 100. You can leave your answer just like this if you want. In this specific case, this simplifies really nicely. This ends up being equal to 4,000 because the square root of 100 is just 10. But I don't need you to write this. If you write this like on a test, you're getting full credit. I mean, maybe tell me it's this symbol. Not a bad idea to show your work, show that you know what the formula is in case you plug in the wrong number somewhere. But I don't know, if I'm indicating answers, that would certainly give you full credit, as would this and this. So we have these three questions. Before we even answer the question that was asked here, this part about what is the probability that. You'll see that happens a lot. Going forward on most problems, you're going to state and justify the shape of the distribution and tell me the center and the spread. Because what you'll see is the further we get into the class, the more complicated these three things get. Shape, center, spread is going to be a very common theme in the second half of the class. You're going to be seeing that a lot. So we're starting it now. Finally, let's answer the question. Let's find the probability. Well, I know that the probability corresponds with the area underneath the curve. And since the probability has something to do with the average of 100 households, it's the area under the sampling distribution curve, not the parent distribution curve. So here's my distribution. I could put the center, mu sub x bar, in the middle here, 60,000. If you felt like it, you could count up and down. Just don't do it by 40,000s. Do it by 4,000s. Because this is the sampling distribution. How do you know it's a sampling distribution? Because it's normal. Right? The parent distribution is not normal. Parent distribution would have been right skewed. Think Steph Curry. This is the sampling distribution, so it's normal. That means that in this picture, I draw it normal with this center and this spread. You could count up and down by 4,000s, but at this point, I figure you're good with that. Like, that's kind of a beginner way to draw your pictures. Typically, what you'll do going forward is you'll give the reader the context, and then you'll draw the picture with less numbers in it. So maybe you'll say off to the side, shape, center, spread. Right, that's what we're going to end up doing. So you don't need to count up and down by 4,000s is the point of all this. The reason why is because sometimes this will be a really ugly decimal. Like, yeah, you're dividing by the square root of 100, which is great, but what if it were the square root of 103? And then this is some ugly decimal, 40,000 divided by some decimal, some ugly decimal. And now you got to count up and down by 3,997.83624, or whatever that number ends up being. You don't want to do that. So don't bother. Just leave it like this. What is the probability that in a random sample of 100 households, the average income is below 50,000? Well, here's 60,000. I'll throw 50,000 over here. It doesn't really matter where you put it. Just make sure it's to the left of the mean. But as far as how far out to the side you put it, I'm not worried. Put it wherever you want. Shade in to the left of that point because we want less than 50,000. And then tell your grader how you're getting that answer. You're getting that answer with the normal CDF function in your calculator. Because anytime you're trying to find the area, you use normal CDF. The normal CDF function in your calculator, it's under the distribution menu. So you hit second and then variables, you turn your calculator on. This one takes a minute sometimes. Hit second and then variables and go down to normal CDF. My lower bound, 0 would be fine. But I've told you that anytime you're missing a lower bound, put in a large negative number just in case. But in this case, if you left it at 0, you'd get the exact same answer. Upper bound is 50,000. All right, that's the top of my shaded region there. The center is 60,000. And then my spread, you can just type it in as 4,000 if you want, but it's not a bad idea to get in the habit of typing it as an expression, 40,000 divided by the square root of 100, because often this won't end up being a nice number like it is in this example. Then you hit paste, or if you had the other version of the calculator, you put in all these inputs in with commas in between them, you hit enter, and it spits out your answer for it. Really small answer. Normal CDF, small number, 50,000, 60,000, and 4,000, or 40,000 divided by the square root of 100. Do all that, and you get less than 1%. So if I move the decimal place twice, I got 0.62%. In other words, it's pretty unlikely. It's very, very possible that one person makes less than 50 grand. Lots of households make less than 50 grand. But if there's 100 households in your sample and the average is 60 grand, the average of my 100 households is probably going to be pretty close to 60 grand. It's pretty unlikely, less than a 1% chance, that it's this far away from 60 grand. That's what we're getting at here in part D. And that's what questions look like in this section. What could I change? I don't know. What if your sample only had 36 households? Right? Maybe this should be in a different color so I don't have to redo all the parts above. What if your sample is only 36 households? The questions are the exact same, but you only have 36 households. What would that change? State and justify the shape of the distribution is the same. It's still normal because n is still greater than or equal to 30. 36 is my new value of n. And that's still greater than or equal to 30. So cool. I can still draw a picture that kind of looks like this. The center, mu sub x bar, is still equal to mu, and mu is still 60,000. That didn't change in the problem. That's this number. So I'm still throwing 60K in the middle here. I still want to know the area to the left of 50,000. So I'll toss 50,000 over here. And then I'll calculate this area. To calculate this area, I need to know what the spread is. Right? So this is the same. This is the same. This is not the same. Right? Sigma sub x bar will be different because it's still sigma divided by the square root of n, but now n is 36, not 100. So it's 40,000 divided by the square root of 36. And I don't know what that is off the top of my head. I mean, it's 40,000 divided by 6. You could ballpark it. It's like 7,000, give or take, a little bit less than 7,000. The point is the spread is bigger. Why? Because sample averages, if there's 36 households in the sample, are going to be more spread out than if there's 100 households in the sample. Right? Think about the boxes dropping from the sky in that applet that we looked at a couple of videos ago. At any rate, if your sample only had 36 households, not much would change. It would still be normal CDF. Lower bound, still a negative bunch of 9s. Doesn't matter how many. Upper bound is still 50,000. Center is still 60,000. But here's where it differs. Instead of 40,000 divided by the square root of 100, it's 40,000 divided by the square root of 36. If you want, this is a useful little time-saving feature. If you hit second and then enter, it brings up the last entry that you had. And note that my current answer should be very similar. If I do 3, 6, and then delete, everything else is the same. All right, all I need to change is the number that goes right here. Now instead of 100, it says 36. I hit enter, it spits out the answer. It's telling me that that's equal to what, like 6%? 6.68%? Sure. And that's my answer. Note 6.68% is a lot bigger than 0.62%. Oh, that makes sense. It's a lot more possible to get this really low, I mean, relatively speaking, household income out of my sample if there's less households in there. Right? The more households there are in my sample, the more likely my sample average will be close to 60,000. That's the idea with this example. What else can we do? I could say in a sample of 36 households, how likely is it? No, let's not do that one. In a sample of 36 households, the middle, I don't know, 90% of averages fall between which two values? What I'm asking you here is to tell me the dollar amounts that the averages would have to be to capture the middle 90% of the data. If you're drawing a picture, you draw something that starts out looking approximately normal. Make sure you understand why. It's because 36 is still greater than or equal to 30. You want to capture the middle 90% of data. So here's 90%. And note that I'm putting it in the middle here. Shade in the middle 90%. Center, still 60,000. That hasn't changed at all. I got to find this number and this number. It's no longer a normal CDF question, right? Because you use normal CDF when you're trying to find the area. I'm not trying to find the area. I told you the area. We're trying to find the numbers that go down here. You have to use inverse norm to figure those out. Inverse norm always takes on three values. The first value is the area to the left of the point you're looking for. So if I'm looking for this point right here, you got to think about how much area is to the left of that point. 90%? Nope. Oh, right. 10%? Nope. 90% is shaded, so 10% is not shaded. So half of it's over here and half of it's over here. Means this side's got 5% and this side's got 5%. So when I use inverse norm to find this value, the area below the point is 0.05, in other words, 5%. The center is 60,000, and the spread is 40,000 divided by the square root of 36, and that's because in this one, my value of n is 36. Second, and then variables, go down to inverse norm. The area below is 0.05 for 5%. The center is 60,000. The spread is 40,000 divided by the square root of 36. Type that all in. Kick out a number for me, 49,034. Say it said round to the nearest dollar. Fine, that's your answer then. Wait, so that's my answer and I'm done? No, that's your answer for this number. But the question says which two values. You got to find this number as well. Well, you can be kind of clever and be like, well, this number is as far below this number as this number is above this number. So you kind of subtract the two and then add it back on to figure out this value. Might be easier, just use inverse norm again. Inverse norm, how much area is to the left of this point? Well, 5% is to the right of it, so 95% is to the left of it. 0.95. And the center is 60,000. And the spread is 40,000 divided by the square root of 36. If you type all that into a calculator, and look, I'm going to be clever here and hit second and then enter to bring up the most recent entry. We'll leave all this the same, and we'll leave all this the same. The only thing I'm changing is instead of 0.05, I want 0.95. Hit enter, spit this number out, $70,966. So the middle 90% of averages of 36, that's important, would fall between 49 grand, give or take, and 71 grand, give or take. So note that just like in 3.1, I could ask you normal CDF questions or inverse norm questions. And for the inverse norm questions, they can be kind of easy where I give you the area to the left of the point you're looking for. They can be a little bit harder where I give you the area of the right of the point you're looking for and you got to find the area to the left. Or the hardest version is like what you saw here where I give you the area in the middle and you got to figure out how much is to the left of each of the 2 points. That's what you're doing in F here. One more example, then we'll call it good. What percentage of households make above 100 grand? All right, maybe you're asked this question. Well, you might be like, all right, what percentage? I'm good with this. This is a normal CDF, right? It's definitely going to be normal CDF if I have to find the area. And my lower bound, I guess, would be 100 grand. And my upper bound, I don't know, I guess a bunch of nines. Let's see, center and spread. Center would be 60 grand like it's been throughout this spread. 40,000. 40,000 divided by the square root of 36. 40,000 divided by the square root of 100. Shoot, I'm not sure what the spread would be. That's a trick question. What percentage of households make above 100K? This is a 3.1 question. This is not a question about the sampling distribution. If I said what percentage of averages of 36 households would be above 100 grand, if the question was about the average of some number of households, it would be a chapter 4 question, but it's not. This is just talking about all households. This is not interested in sample averages. This is a question about the parent distribution. It's a 3.1 question. So you're like, oh, okay, so I can just do it and leave my spread as 40 grand. No, actually, because in order to be able to do G, it has to tell you that the shape of the parent distribution is approximately normal. So if I said, suppose household income is approximately normal, and the mean is 40 grand and the standard deviation is 60 grand, then I can ask you chapter 3 questions like this. Then you could do this. But without that assumption that the parent distribution is normal, we can't do chapter 3 questions. In every single chapter 3 question, you have to be told that the parent distribution is normal. Otherwise, you can't do it. So there's supposed to be 2 things to get out of example G here. The first one is to be careful. When you're in the chapter 4 homework, you'll see that most of the questions are about the sampling distribution, but they throw in parent distribution questions in there as well. And you're like, oh, that'll be easier. That'll make my life easy. They'll tell me mu and sigma, and I'll just use inverse norm and normal CDF. I won't have to worry about these formulas at all. Yeah, that's true, but it's kind of tricky that they're out of place. You'll be looking at these and be like, where's n? I got to find n so that I can use this formula. Be careful. Some of the questions in 4.1 really belong in 3.1. But we'll talk about that when we get to the homework and flip through the problems. The other point that I wanted to make is when we're dealing with the parent distribution, you don't have a value of n. And if you don't have a value of n, you can only get normality if it says the parent distribution is normal. So you'd never be asked a question like part G if this were the prompt that you were given. That's all I got for chapter 4.1.